Thank you, Vanessa. Can you hear me? Now it should be better. Can you hear me now?
There we go.
Thank you. Thank you, Vanessa. Yes, I'm Bertrand from JPL. I'm the Deputy Product Scientist for Raman at JPL, and I've been asked to come and talk to you about the Raman Coronagraph instrument, telling you a little bit about the expected capabilities of the instrument and how they might be of relevance to this mission you probably all heard about, which is HWO. So just a little bit of an outline. I will start by talking to you a little bit about the Raman Coronagraph, high-level specifications of the instrument. Then I will go through all of the observing modes that are on the instrument, some being guaranteed, some being best effort, and some being at this point unsupported, but they are in there. The hardware is there, so we hope at some point we can use it. If the hardware is not there, then you know you're never going to use it. And then I'll talk a little bit about the INT lab results that we got, which is why we want to tell you a little bit more about the capabilities of the instrument, not in theory, but as measured in the lab earlier this year before we shipped the instrument to Guarded. And so, related to that, what are our expected in-flight performance? And there's a range of performance that we can expect for the instrument. And corresponding to this range of possible performance, there's a range of potential science applications that we could pursue with the instrument, so I'll touch upon these as well. And then finally, I'll tell you a little bit about the opportunities for community participation via the ongoing community participation program, the CPP, but also more generally outside of it. All right, so in a nutshell, the Raman Coronagraph is, of course, a stepping stone toward a future mission. We used to say future mission. We do have one now on the horizon, so I can replace future mission by HWO. So this is becoming even more relevant now that we have this mission on the horizon. And the Raman Coronagraph is a visible light, high contrast tech demo instrument for HWO. It will be the first space-based coronagraph with active wavefront control. We've flown already a number of coronagraphs on other telescopes with passive coronagraph, if you will, with no active control. So that will be a big change. Our single technological requirement is fairly modest. It's to reach a 10⁻⁷ detection flux ratio limit at a 6 lambda over D separation in a single photometric band. And you'll see that we demonstrated a lot better than that, and we hope to do a lot better than that in space. And I'll get back to that a little bit later in this talk. In practice, it looks a little bit more messy than in the previous slide, which was just a CAD drawing. But that's the reality for you. That's a line optical bench in the high bay at JPL before we tested in vacuum. There's a number of optics here that you may recognize. Some of our deformable mirrors. I'll try to show one of them here. Then once you have this aligned optical bench, which, by the way, we got fantastic wavefront quality all the way through the system, I believe less than 30 nanometers RMS. 40? Thank you, Vanessa. You can see on the right here as well how this optical bench, which is about the size of a piano, is on top of the electronic palette. And once we assembled all of this, we put it in the test bed, in the vacuum chamber. So focusing a little bit on these key technologies that HWO will demonstrate. Of course, there's low order and high order wavefront sensing and control. For line of sight control, we've got this fast steering mirror, which is actually inherited from the old SIM days, believe it or not. We got a focus control mechanism here, which is extremely precise. We got a pair of DMs, deformable mirrors, and as you know, we need two of them. One is in a pupil plane, another one is actually a quarter of a Talbot length away in a non-pupil plane to be able to correct not only phase defects but amplitude, which is necessary in order to get to this 10⁻⁷ and better raw contrast levels broadband. We also are going to demonstrate high contrast choreographic masks. You see here some pictures of the two types of masks that have been manufactured for the Roman chronograph. The top one is pupil masks, so they are actually pretty easy to see because they are about an inch in diameter. And the other ones are the hybrid Leo chronograph mask, and we have a series of them. And they are, of course, here, tens of microns wide and much smaller. The other technology that obviously we're going to be demonstrating with the Roman chronograph is photon counting visible detections with two EMC CDs, almost identical except for the rates at which they're going to be read. One is for the science camera. It's probably read every 100 seconds or so, and one is for our low-order wavefront sensor, for which we're going to use much faster rates. And then, eventually, we're going to get this data with starlight speckles, and we're going to try to process them as well as we possibly can. And it's a really big topic, and that is responsible for a lot of the uncertainty at this point in terms of the final detection limits we could get with such an instrument. We've seen in the past with HST, NICMOS data, HRS 799 data, or more recently with JWST, that post-processing can actually gain you a lot of quality in terms of contrast that you can detect. So that's going to be also a big topic to try different data post-processing techniques once we have this space-based chronographic testbed. A few more details about the optical layout, just to call some of the different parts that I've shown to you before. Here is the fast steering mirror, sorry, here. Actually, I think I have circled them, so it's going to be easier. The 2DMs are here. This is the pupil and focal plane mask that I just showed you, and the two detectors. And what you can see in the middle region here is the three major modes that we have. So we have a single optical path, and we have 6 different planes with precision alignment mechanisms which are being used to select one mask or the other, one filter or the other. And so a given mode is actually a combination of all these positions for all of these 6 masks. And you see here 3 main modes. The narrow field of view mode, which is basically using the hybrid Leo chronograph and looking very close in. A spectroscopy mode, which will use a slit spectrograph and only nulling part of the field around the star. And what we call the wide field of view mode, which extends all the way to 20 lambda over d, which is using a shape pupil chronograph. So here are these modes again. NFOV, spec, wide field of view modes. And we have a bunch of other modes which are at this point unsupported, meaning that they have not been tested in TVAC, in thermal vacuum, and there are no guaranteed support at this point on orbit. And you'll see also that we have best effort modes, which have been tested to some degree. And technically, we have only one required mode, which has been fully tested and demonstrated, and that's the narrow field of view mode. So these are the different modes that are going to be available with different levels of risks. So this is what it looks like when you bring the vacuum chamber. Believe me, it did fit in. The optical bench, the telescope simulator, the radiators for the optics and the control electronics. And cutting to the chase, here are the results that were obtained after weeks of operations in the vacuum chamber, but only a small duration dedicated to what we call dark hole digging. And you see that we did not only pass our requirement with one mask, the HLC mask in narrow field of view mode, but we also did pass it with the other mask, the SPC mode on the right. So the requirement was to get to a detection limit of 10⁻⁷, which almost translates to a raw contrast of 10⁻⁷, more or less. And we actually did about 3 to 4 times better, depending on the region of interest. The requirements only called the annulus, which you can see here, between 6 and 9 lambda over d, and same here on the other coronagraph, but we actually did much better. For the HLC mode, we were getting this type of contrast all the way from 3 to 9 lambda over D, 10% bandwidth at 575 nanometers. And for SPC, same 10% bandwidth around 575 nanometers, but now much more extended from 6 to 20 lambda over D, both polarizations. Just a little animation to show you how we dig the dark hole and we converge to a very deep dark hole over time. Got a bunch of superheroes here that I want to give credit to, because these people and many others have been key in getting these results, and it was by no means easy. It's been a lot of work in TVAC to get to that type of results. An important aspect of this, and I could show you the curves if you're interested, is that we were still getting slowly better results when we decided to stop because of time limitations. So we feel like this currently demonstrated performance, which was already 3 or 4 times better than the requirement, is not the ultimate performance that we expect for the instrument. It's not fundamentally performance limited yet, just time limited. And even more for SPC, where we spent much less time, because it was really a bonus observation that we could make. So what does that mean in terms of detection limits for the Raman coronagraph? You might have seen this curve many times in the past, but I will still explain to you what it is. The usual plot of flux ratio detection limit, so it's an astrophysical quantity on the y-axis versus separation in arc seconds. You can see different instruments here and their performance in space or from the ground, and then concentrating on Raman itself. This is our unique requirement, which is to reach a 10⁻⁷ detection limit at 6 to 9 lambda over D, which corresponds to about 0.3 to 0.5 arc seconds. And then the predictions that we made 3 years ago, based on initial testing of subcomponents or sub-coronagraphic benches, for 3 modes that I mentioned before: the wide field of view mode, the narrow field of view mode, the spec mode, and the wide field of view mode. And so that is basically what we would expect to get to if we put all of the modeling uncertainty factors to 1. So that's kind of the best case scenario. And what we got in TVAC in limited time is kind of an upper limit. TVAC is thermal vacuum testing. So what we know is that basically the performance of the instrument, as much as we can anticipate it now in space, will be in between these 2 blue curves, the dashed one and the solid one, so in that yellow region. Where we're going to be exactly is going to depend on a lot of factors, but I think that would be my guess as to where we're going to end up with Raman, with that particular narrow field of view mode in the future in terms of detection limit in space. I told you already, this has been moved from the Raman coronagraph instrument has now been moved to guarded for integration with the rest of the payload and the observatory for our launch, which is supposed to happen before May of 2027. And so we have all the team here, and everything went well. They crossed the US in that truck over 3 days, no pressure. So a little bit about the schedule. So we just delivered the instrument to Goddard. Our launch, I said, May 2027. 2 years ago, we learned that we were going to fly with a SpaceX Falcon Heavy. The tech demo phase is, sorry, I skipped the commissioning. So we're first going to have a commissioning phase for all of the Raman observatory, testing basic functionalities of survived launch, including about 20% of the time for making sure the Raman coronagraph instrument is behaving the way we expect. At the end of that 90 days of commissioning, we start what we call the technology demonstration phase for the coronagraph, which is supposed to happen during the first 18 months of the mission. And we have about 3 months allocated to that tech demo phase for the Raman coronagraph. Not continuous 3 months, 3 months spread out over the first year and a half. Our top priority, obviously, will be to achieve the L1 requirements which is the 10⁻⁷ detection limit, but we hope to do a lot better than that. And as time resources allow, after we've demonstrated that basic requirement, we'll try to push the performance limits, with the guiding principle for decision making being that we want to maximize the long-term value to the science community and to the Habitable Worlds Observatory preparation. In order to maximize the value to the science community, we'll try to use some scientifically interesting targets whenever possible. And if the technology demonstration phase is successful, we certainly hope and anticipate there will be some potential for follow-up observations after the first 18 months of the mission. That remains TBD. So what kind of scientifically interesting targets we could envision for this mission? No surprise. This came also from analysis that was done by our science investigation teams a number of years ago. Exoplanets of different types, self-luminous or reflected light observations, bright debris disks, and faint debris disk detections. So I'll go very quickly through each of them to give you a flavor of what might be done depending on the exact performance of the instrument. In terms of young self-luminous planets, Beta Peak B being an example, and many others like Epseri and so on, the questions that we hope to answer with CGI, and which would probably be able to answer at 10⁻⁸ contrast, are what are the cloud properties of young massive planets? How inflated are they? Are they metal rich? We may even be able to look for sodium and potassium in their atmosphere. What you see in their SCDs here, obviously, is that as you go from the near infrared to the visible, these hot planets start to really get faint as you go to shorter wavelengths. So HST has observed Beta Peak B at, I think, 950 nanometers, something like that. That's the only one. So we hope to bring a lot more of these self-luminous planets to observations, photometric observations in the visible, and maybe down all the way to 700 nanometers. Short of that, you really have not a lot of light. So we hope to observe 1 or 2 systems during the TDP, tech demo phase, and cover additional band passes and more of these known self-luminous planets during extended phase. In terms of mature Jupiter analogs, so colder Jovian planets, the questions we're going to try to tackle are cold Jupiter analogs cloudy or clear? We could potentially see that from photometry. We're going to be observing non-RV giant planets, so that means that with observations over 2 or 3 epochs, we should be able to constrain the inclination and then the mass, given the RV data. Once again, 1 or 2 planets during the tech demo phase, additional ones and bands during the extended phase. Spectral characterization of a mature Jupiter analog, that's going to be really at the edge of what we anticipate we might be able to do with Raman. That will really also depend on the size and exact albedo of these planets at visible wavelengths. But if we are fortunate enough, we should be able to do that for 1 or 2 planets. And here the goals are fairly modest scientifically, is to really coarsely constrain the metallicity of these objects. You can see here spectra for different metallicity levels, which are far higher than the sun, from 4 to 30 times solar. We could see these differences. And that would be through spectroscopy at 730 nanometers or around that, looking for methane absorption features, for instance, and possibly also at 660 with a weaker methane absorption feature. Where I think the Raman Coronagraph will shine is in terms of debris disk observations. Very clearly, for planets, you have some kind of threshold. You really need to get to a few 10⁻⁹ to be able to observe these mature planets. If you do much worse than that, you will not see any of them. For disks, it's a very different problem. We have a continuous range of possible dust opacities. So you could imagine disks at from 10⁻�3, 4, 5, all the way to 10⁻⁹ flux ratio levels per resolution element, depending on dust density. So there's going to be a lot more disks than planets that are going to be revealed by these observations. What's interesting is some of these disks, very extended disks, have already been observed by HST, but they are very bright, and we only look at the outer regions. So what we hope to do here is look at the same disk, so we know where to look, but very closer in, so that we can look at the inside regions of these disks. We can look also at fainter disks. What's interesting, obviously, here is that we're going to cross a kind of physical regime in debris disk, which is when you are at opacity levels of 10⁻⁷ or so, or lower than that, the disk structure is not dominated by collisions, but by transport phenomena, resonances with planets, etc. So there's going to be a whole new field of disk imaging in scattered light that we haven't touched upon yet because of limits in dynamic range. Polarimetric imaging will be possible as well. And one that is close to my heart is the ability to do exospherical dust imaging at visible wavelengths. For me, that's one of the elephants in the room when you talk about HWO detecting exo-Earth, is how bright are these exospherical disks at visible wavelengths. We really don't know. We have measured exosody brightness levels in the mid-infrared with the LBTI at 11 microns. But when it comes to the brightness of these exosody structures at the wavelengths of HWO, from the near UV to the near infrared, we don't really know what to expect. Fortunately, the Raman narrow field of view instrument on the coronagraph should be able to answer that question for about 75 nearby FGK stars for which we can access the habitable zone, maybe the outer edge of it, but still the habitable zone. And so it would be a great survey. I'm a big proponent of conducting such a survey. Maybe a small example, a few targets during the tech demo phase, and if we do well enough, I think that could motivate a whole survey after the tech demo phase of 25, 50 targets. All right, protoplanetary systems, H-alpha observations. We cover H-alpha with the spec mode, so that could be very interesting. There's a lot of cautionary tales about observations of these protoplanetary planets. We heard about it this morning. High spectral resolution or spectral resolution high enough to look in and outside of H-alpha lines will be interesting, and is really key to understanding what you're looking at. All right, so let's switch now to community engagement and how we best kind of engage the community in observing and observation planning for the Raman coronagraph. So we have the Raman community participation program, which is chaired by Vanessa and Dimitri Savrinsky at this point. I don't have a lot of time, apparently, so I'm just going to go through this pretty fast and tell you that there's been a number of proposals selected with the PIs indicated here. They cover a wide range of possibilities or of topics in order to help us get the most of the Raman coronagraph, either scientifically or in terms of engineering and preparing for HWO. So I don't have the time to go more into the details here, but you can see that list here. And I think this CPP is selected for typically 5 years, something like that. 4, right. Okay, so that's going to be my last slide. As a summary, the coronagraph has matured already multiple key technologies to lay the foundations for HWO. We're going to learn even more, of course, when we operate it in space 3 years from now. Probably before HWO enters phase A, which is the right time. We're going to get all of these lessons learned before HWO flies, or enters phase A for sure. The testing in the lab under vacuum, TVAC testing, demonstrated performance at least 4 times beyond requirement, and once again, it was time limited rather than performance limited. We even had time to test some of these best effort modes, and the results were very encouraging. In fact, HLC was behaving almost as well as HLC, and much less time devoted to it. The CPP science team will support observation preparation, and will inform and solicit feedback from the community on target selection. So these mechanisms are not yet defined, but we'll get back to the community at that point. And the main message here, I think, is like we saw with previous mission, like HST or JW, the full observational potential of the Roman coronagraph will go beyond what we can imagine today, these little science investigations example that I showed you, and it will be for you to realize them and push the instrument to its limits. And with this, I will thank you and take any questions.
Yeah, perfect. Thank you for leaving so much time for questions. So what questions do you have?
Hi, Bertrand. Aniket Sanghi from Caltech. Thanks for the great talk. So the TVAC results show that the contrast is much better than the requirements. I was wondering, is there any specific area in instrumentation or technology that really contributed to that? And whether is that teaching us something about how we might approach HWO as well?
So I think the philosophy for this tech demo has been to put some requirements that were fairly modest. There's a whole history behind this. We used to have requirements that were a lot more stringent. And at some point what we realized is that no matter what, the engineers were going to build the same instrument, whatever the requirements were, because we were changing them pretty late in the game. And in a way, you know, it's also kind of useful to have requirements which are fairly modest, so you can really show pretty easily that you're going to meet them. So in terms of working with the engineers and management, etc., having some requirements which are a little bit more modest helps going through the different hurdles and limit bureaucracy, to be honest with you. So we kind of always anticipated that we would meet requirements with flying colors. We still don't know exactly what the ultimate performance will be, but I think that 10^8 detection limits at 3 lambda over d is really within the realm of this instrument once in space.
Thanks. More questions?
Hi, Bertrand, great talk. I was wondering, so is the Roman CGI going to always be speckle limited, or at 1 arc second, is it background limited?
Yeah, that's a good question. I haven't thought about that. Yeah, I mean, you know, our detectors have no readout noise, but they still have some dark current, so that may be where we see it. There's also one thing, which is you notice that these dark holes don't go infinitely dark. It's like a U-shape kind of. So even if you are at the edge of the control location of the DM, you're still not doing much better than you would at, you know, mid-range in the dark hole. So they still quite a lot of starlight residuals.
I think we still have another minute or two for questions. Are there more in the room or online? Okay.
On Vega, it'd be interesting to see what limits us. Yeah.
Thanks for a nice talk. Guillaume Bordaro, MP Garching. You touched a little bit the topic on the wavefront error for Roman. How would you extrapolate it for HWO in terms of performances?
Yeah,
based on the current...
That's a really good question. So in 2020, we published a paper trying to tackle this, trying to compare the CBE, or the current best estimate of wavefront corrections for Roman, trying to compare that to what we would imagine would be the requirements for a future mission. And it's a difficult exercise because the requirements of a future mission are not exactly set yet. And it's also a tough exercise because we only have current best estimate for Roman, but now we've got better results from TVAC. And so I think the answer to your question, so we want to revise that paper, which kind of showed that in many respects, even though we are only at 10^8 versus 10^10, it's almost as hard to get 10^8 with this entrance aperture than it is to get 10^10 with a more coronagraph-friendly aperture. So what that paper concluded at the time is that at least for low-order wavefront sensing and correction, what we are able to do on Roman and demonstrate should be good enough in many ways for HWO. Now HWO will be very different. We know it's going to be probably a segmented aperture, so there's a whole slew of new issues that we haven't really factored in or had to deal with. But if the telescope is as stable as it is for Raman, on the low order wavefront side, we should be performing at the right level. Higher order aberrations, it might be a different story. But anyway, we're going to have to revise all of these previous calculations now that we have TVAC results. And that takes me actually to the highlighted bullet here, which is that at the end of August, here again at Caltech, at IPAC, we're going to be organizing an info session that's basically going to present all of the results from CGI and TVAC and put them in perspective of HWO. So if you're interested, please register.
Excellent. Yeah, well, thank Bertrand again for an excellent talk. And now we'll